some recent results which are associated with the ability to represent deterministic delays in stochastic models. Okay. So basically, for a long time period, the natural way to represent deterministic delay in stochastic models was the use of phase-type distribution, and inside the group of phase-type distribution, a special phase-type distribution, which is the series relation of consecutive exponential phases, which is also referred to as Erlang distribution. And it is known that the coefficient of variation, or the squared coefficient of variation of this structure, is 1 over n. So if we are considering n consecutive exponential phases, then the coefficient of variation is 1 over n. So we can represent a deterministic delay, or we can represent a delay whose coefficient of variation is as low as 1 over n. In this talk, I'd like to recommend to replace this approach with a different approach, which is somewhat similar with respect to the underlying analytical treatment, and somewhat more general because it allows a much lower coefficient of variation. This more general approach is due to the family of matrix-exponential distributions, and as I'm going to present, the squared coefficient of variation of the matrix exponential distribution is can be as low as 1 over n squared. And basically, during this talk, I'm going to introduce how this low variance matrix exponential distribution can be obtained and what can we use them for. Basically, the title of the talk, which is a concentrated matrix exponential distribution, comes from the fact that we are looking for matrix exponential distributions with very low coefficient of variation that we refer to as concentrated. So basically, after a short introduction, we are going to have some part of the talk which is devoted to the way to obtain matrix exponential distribution with very low coefficient of variation. And after that, I'm going to present two application area in stochastic modeling where we can make use of concentrated matrix exponential distributions. One is the transient analysis of various stochastic models, and the other is inverse Laplace transformation. Oh yeah, last time I learned that we can play this game. Like if I want to emphasize something, I think this is going to allow you to see where my cursor is. So, okay. So let's start with a short introduction on phase type and matrix exponential distributions. Okay, in this talk, I am starting from the more general one, which is the set of matrix exponential distributions. Matrix exponential distributions are defined, as the name indicates it, by a matrix exponential function. Over here, we have got a square matrix A, and this is E to the AX is this matrix exponential function, which is indeed a matrix. But whenever someone multiplies it with a row vector from the left and the column vector from the right, then it results in a scalar function of x. And over here we have got the dimensions. So n, the matrix A is a square matrix, n times n. Vector alpha is a row vector, 1 times n. And this column vector 1 is a column vector of dimension n, and it is composed of ones. So it is a kind of summing up column vector. In case of matrix exponential distributions, there is no sign restriction on the elements of vector alpha and matrix A, which means that both of them can contain positive and negative elements in any position. Unfortunately, it is rather hard to evaluate if a matrix exponential is a function of this kind is non-negative. So basically, the main difficulty of working with matrix exponential functions is that this matrix exponential expression is not necessarily non-negative. So vector alpha and matrix A can represent a function which goes negative at some x points, and if it is the case, then it is not a distribution. So basically, there is a very complex restriction on vector alpha and matrix A to ensure that fx is non-negative, and due to this complex restriction, the use of matrix exponential distribution has been limited for a long time, and still it is a challenging problem to find proper vector matrix pair which ensures that fx is non-negative. Anyhow, having vector alpha and matrix A, one can compute several properties of the distribution, like the moments, and based on the moments, one can compute the squared coefficient of variation. It is important to mention that the squared coefficient of variation is, especially as it is defined here, is a property of the distribution which is insensitive to scaling and multiplication. So basically, with any positive constant C1 and C2, this relation holds. It will have some importance later on when we are going to play around with the number of parameters of the matrix exponential distributions. So basically, this is the set of matrix exponential distribution, and one very efficient way to obtain a vector alpha and matrix A, which ensures a non-negative fx, is the restriction of phase-type distributions. So if alpha is non-negative and A is a generator matrix, meaning that the off-diagonal elements are non-negative and the diagonal elements are negative, then this alpha A pair is going to represent a Markov chain or a transient part of a Markov chain, and as a result, the associated fx is going to be non-negative. This fact that the density function is non-negative if these sign constraints apply has got very beneficial consequences, and one can freely play around with all vector alpha and matrix A without violating the non-negativity constraint. The limitation which plays role in this talk for the phase-type class is the fact that somehow the phase-type class is restricted in the squared coefficient of variation, and there are some well-known and quite old results which says that the squared coefficient of variation of a phase-type distribution of order n is not less than 1 over n. So basically, this is the limitation which force us to play around with matrix exponential distribution instead of just using this very familiar set of distributions, the set of phase-time distributions. So how to obtain concentrated matrix exponential distributions? Indeed, it is an optimization problem. In this optimization problem, initial vector alpha and matrix A defines the fx function, and the fx function, as it was presented 2 slides before, characterizes the squared coefficient of variation. So the optimization problem, which is a nonlinear optimization problem, is to minimize the squared coefficient of variation for a given initial vector alpha and matrix A, such that the non-negativity constraint applies. And basically, this constraint is the one which makes this problem very, very difficult to solve. Indeed, till now, we don't have a proven solution for this problem for n larger than 2. So due to the difficulty, especially of this constraint, people started working on workaround approaches. And one of the most promising workaround approach is to search for the minimum in a special subset of the set of matrix exponential distributions, which is non-negative by construction. There are many such subsets of matrix exponential distributions, but the one which is most promising for us and was used for generating matrix exponential distributions with rather low coefficient of variation, even for high order, is this class which we address as the exponential cosine square family, or cosine square function. So basically, this function is also a matrix exponential function, but due to this construction that it is the product of non-negative cosine square functions, it is ensured that the associated matrix exponential function is non-negative. So this is a nice family, but it has got two still weaknesses or disadvantages. One is that it is not, not proved that the minimum coefficient of variation of the matrix exponential class falls into this set of functions. It is still a conjecture which is studied for a long time, and no counterexample has been found yet, but it is not proved. And the reason why it is difficult to prove is that it is still a function, family of functions for which the minimal coefficient of variation is obtained by some optimization. And basically, we need to prove the minimality of a function which is obtained by some optimization. So, oh yeah, so first of all, one comment on why is it a matrix exponential function. Basically, if one applies a trigonometric exponential transformation of this set of functions, then one can obtain this kind of exponential representation. And this exponential representation will have some very important application later on. But over here, I just would like to mention that these eta k and beta k parameters can be complex. So it is an exponential representation of the same set of functions, but the parameters can be complex here. So basically, we have got somewhat similar problem as it was present already with phase-type distributions, that we have got more than one representations, and one representation is beneficial for one reason, and the other representation is beneficial for another reason. So basically, if someone look at a function like that, cannot be sure that it is non-negative. But if someone takes a function like this, it can be sure that it is non-negative. So basically, the non-negativity of this function is ensured only for those eta k and beta k which are obtained from this representation. So anyhow, having this representation, the optimization problem simplifies to, let me say, an optimization problem with some non-negative parameters. So over here, we need to optimize these omega and associated phi I parameters such that the coefficient of variation of this function is minimal. I colored these two parameters, C and eta, because over here we can neglect the effect of these parameters, because I mentioned that the scaling and the multiplication of the function with a given number does not affect the coefficient of variation. So that's why we have got only this many parameters to optimize for finding the minimal coefficient of variation. Yeah, still, so it is a much nicer optimization problem, but the solution of this problem is still rather difficult. There is no symbolic solution for this optimization problem, and numerical optimization are required to solve it. Over here, I'd like to present some results which are which got available during the last decades about the solution of this optimization problem. In 2006, there were results available up to order 17, and these results were obtained by the built-in optimizer of the Mathematica program package. Later on, a kind of evolution strategy algorithm is used to replace the Mathematica, the built-in optimizer of the Mathematica package, and using these implementation, these kind of results had been obtained up to order 74, and actually up to this point we can already draw some consequences on the behavior of the decay. So basically plotting these minimal coefficient of variation results on the log-log scale, results in this curve, which is indeed similar, very, very close to this n2 over n square curve. So up to order 47, we had got numerical results, which were already indicating that we have got a much sharper increase than the sharper decrease in the coefficient of variation than the decrease in the phase type class. Anyhow, our aim was to go for higher orders. And in order to go for higher orders, we needed to solve some computational issues. So basically, we had to look for an efficient procedure to compute the coefficient of variation based on the parameters. And it has to be accurate and efficient because during an optimization procedure, the coefficient of variation has to be computed many times for various parameter sets. And we need efficient optimization procedure. So let's consider these two problems one by one. So first, the efficient computation of the coefficient of variation based on the parameters. So we were working with this representation for a period of time, and it turned out that computing the moments is very simple if we have got these exponential representation of the same function. If we have the exponential representation, then the moments can be simply computed based on a very simple operation of the parameters. So it turned out that the main problem got to be to transform this cosine square representation to the matrix exponential representation, again in an accurate way. I keep mentioning this accurate way because as the order increases, we are facing problems of numerical accuracy using standard double precision arithmetic. Anyhow, the main result which allowed us to resolve this problem was this kind of transformation. So basically, from the cosine square representation, we can transform the function to this matrix, to this exponential sum representation, in which we have got complex variables. And by resolving the complex variables, we can represent a real representation of the same function using these A, Kn, Bkn, and Ckn parameters. And the key results over here was to obtain these A, B, C sets of parameters with some iterative procedure. I think it is meaningless to devote too much time to this expression itself and the derivation of this expression, but the main thing is that it is really an iterative procedure which starts from some boundaries and it computes the parameters according to this iterative scheme. And when we were, based on the iterative scheme, one can easily compute the moments and gets the representation. The main problem with this approach, which turned out to be important, or the main, we have to pay attention, is the numerical accuracy. So it turned out that during the execution of the iterative procedure, quite high accuracy loss, precision loss occurs. And in order to cope with this precision loss, computation, the implementation of this iterative procedure has to be done with sufficient precision. Over here, we came up, according to just numerical experiences, we came up with some expression which indicates the required precision to compute the parameters of the exponential representation. So basically for order whatever, for example, order 60, we have got these 40-digit precision loss. So one have to apply, have to perform the computation at least in 60-digit arithmetics in order to obtain relatively accurate results for the parameters. And that is, so basically the whole iterative procedure has to be performed in high precision, but whenever we completed the procedure, the parameters obtained, A, B, and C parameters are enough to store in standard precision. So basically, one important thing here was that the iterative procedure has to be performed with high precision according to the curve of the precision provided before. And the rest, whenever we have got the A, B, and C parameters, these can be stored in standard double precision, and all computation or consecutive computations can be performed in standard double precision based on these parameters. The next problem was the efficient optimization. And over here, I just would like to mention that we considered various kind of evolution strategy procedures. And basically, we had got two extremes, which is the CMES procedure and the same procedure with a kind of population increase in the meantime. And these two procedures differs in their accuracy and also in their time to evaluate the optimum. So basically, this procedure with population increase requires enormously large time, but in many cases, the results we obtained, I mean the coefficient of variation we obtained, we consider to be optimal, meaning that, I mean, looking at the results of the consecutive optimization consecutive optimizations for different orders, we had got an impression that up to 74, this procedure, which takes quite large time, resulted in really the optimal parameters. Anyhow, for larger orders, we still could use the CMES procedure, which is much faster than the same procedure with the population increase, but the results we obtained was found to be suboptimal. Over here, we have plotted the location of the phi parameters. So basically, if one looks at this procedure, I'm sorry for this. So multiplying ft with et results in a completely periodic function. And inside this periodic function, due to the fact that we divide this numerator by 2, so this phi I is periodic. Okay, so this phi I is subject to any addition of 2 pi. So if pi I increased by 2 pi, it will result in exactly the same function. So we are looking for the optimal pi I in 0, 2 pi. And that is depicted here, where the optimal pi or phi values are located for various kind of orders. Basically, what we can see here is that up to, like, I don't know, 14 or 15, the pi's are located left to a kind of gap. So basically it is such that whenever these phi parameters are obtained, the function is going to be 0 at that point. And in order to suppress this part of the function, we need to allocate a lot of pi values left to the main peak. And for low orders, the exponential term, the exponential decay, suppress the function after the main peak. But for higher orders, it starts to be beneficial to suppress the function with some zeros of the cosine square function. So basically, this interpretation to gain costed us like 10 years. But whenever we had got this interpretation, which was due to the fact that we could evaluate the minimum up to order 74, so due to the, I mean, this interpretation, we had got much better chances to go beyond the limits of the optimization procedure. Basically due to the fact that we have got an intuitive interpretation of how this optimization procedure works. So basically in this small gap, we have got the main peak of the function, and on the left of the gap, function is suppressed by these zeros which are located here. On the right of it, it is in the first period up to 2p, it is suppressed by the zeros here, and after that, in the next period, it is suppressed by the exponential decay. So it is a very nice optimization, and the optimization procedure which needs to find these phi I parameters is such that the number of parameters to optimize is n+1. So this way, the complexity of the optimization procedure increases by n, and as it increases by n, it gets to be very complex when we would like to compute concentrated matrix exponential distribution with orders larger than 180. So basically, this 180 was the limit where this CMEAS optimization procedure gets to be prohibitively slow. So what to do beyond this limit? How can we utilize the information we learned from the location of the optimal procedures? So over here, we have plotted the location of the optimal phi parameters for order 74. In this particular case, we have got 4 zeros above the main peak and this many 70 zeros below the main peak. And that's the structure this function has below and above the main peak. And we would like to go beyond the limit of optimizing all of these parameters. So the main idea to go beyond this limit was to approximate the behavior of these discrete function somehow with a familiar function and optimize the parameters of that familiar function. We picked a very simple function, a polynomial function, so we assume that the phi I below the main peak is a polynomial of this structure with parameters small theta, small gamma, and small a, and above the main peak it is big theta and big gamma and big A. So basically, assuming that phi I follows this function allowed us to approximate all of these phi I parameters with a limited number of parameters. Okay, basically, whenever we were looking for the optimal setting of these parameters, we figured out that the location of the gap, which is over here, and the size of the gap, which is over here, we have got the difference of the consecutive phi values. So the size of the gap, which is here, might be easier to cope with, and it is more meaningful when we look at to the parameters of the procedure. So by this reason, we apply the kind of parameter transformation. So we said that the last phi parameter before the gap should be this one, the last parameter after the gap should be this one, and it should be that the function applied for the next parameter should be 2 pi. So this way we locate n pi values in between 0 and 2 pi. Anyhow, it is just technicality, but the main point is that as a result, we obtained an optimization procedure with this many parameters. So we have got this I star, which characterizes the number of zeros before the main peak. We have got the smallest phi values. We have got the location of the main peak and the width of the main peak. So the width of the phi parameters at the main peak. And we have got the shape parameters before and after the main peak. Altogether, it is a 6-parameter procedure, and basically for any number n, independent of the order, we have got a 6-parameter optimization procedure. Basically, for this 6-parameter optimization procedure, we also apply the CMES method, and what we can see here is that up to this limit, we could compute the optimization procedure of all the phi parameters. And beyond that limit, we just couldn't make further on. But with the help of this heuristic 6-parameter procedure, we obtained a simpler optimization problem, which allowed us to extend the results up to, according to this curve, up to 2000. Actually, right now, we are around like 10,000. We can compute these low order or concentrated matrix exponential distributions up to 10,000, whose which is 10 to the 4, whose coefficient of variation is less than 10 to the -8. Okay, so this much, oh yeah, I was just mentioning this. So this much about the generation of concentrated matrix exponential distribution, and let's see the potential application of these distributions. The first application field which I'd like to mention is the transient analysis. Basically, there are many stochastic models in which it is much harder to compute the transient behavior of the model than the stationary one. And I don't know if it was the first paper, but in this paper, Van Hout and Bondia recommended a workaround approach, recommended an approach by which the transient analysis results can be obtained with the help of the stationary distribution. So basically, the approach is the following. We need to extend the model with a random clock, and when this random clock expires, okay, we run the model, actually at time 0, we start the model as it would start without the clock, and we also start the clock. When the clock expires, we reset the original model to its initial state, and we reset the clock to this initial value and repeat this cycle. So basically, this extends this single transient period to be an infinite cycle of transient periods. Basically, it results in a process whose stationary distribution has to be computed, and based on the stationary distribution of the extended process of this circular process, one needs to compute the stationary measure or the transient measure of interest. So basically, in this case, the transient measure at time t. And this approach indeed was used in the literature several times, and time to time, when they did this approach with defining the clock as a phase-type distribution, or better to say as an Erlang distribution, then the procedure was referred to as Erlangization. Anyhow, if the clock has got low coefficient of variation and the mean of the clock is t, then the procedure obtained this way approximates the transient behavior at time t based on the stationary distribution of this complex model. So we would like to apply this approach just to explain how it works for the simplest possible stochastic process for a continuous time Markov chain. So let's assume that we have got a continuous time Markov chain with generator Q and initial distribution pi. And in this case, the transient behavior at time capital T can be obtained as pi to EQT. Of course, it is easy to compute, and there are procedures to compute this quantity, but in order to indicate the behavior of the process, we are going to go along this procedure of extending the model with the clock. So we assume that we have got a clock with a probability density function alpha EAX times vector A, where vector A is just this column vector, which can also obtained from matrix A. So it is a matrix exponential function, and using this matrix exponential function, we can generate, and using the fact that this original Markov chain is characterized this matrix Q, we can generate a stochastic process which characterizes the behavior of the two things together. This extended Markov chain will have got this structure. We have got the original behavior of the Markov chain characterized by matrix Q until the random delay characterized by matrix A and alpha expires. So over here, the behavior of this model is such that in this period, until the random clock expires, the model behaves according to generator Q. Whenever the clock expires, there is a transition characterized by this vector A, and the process moves to an extra state, which extra state is used for resetting the process into its original state. So this we can be chosen with any rate, but as a default we can use rate 1. So if it is rate 1, then we spend an exponential distributed time with parameter 1 in this additional state. And after this time expires, the model rises back to the initial state, and it starts the next cycle, which is the same, statistically the same length, so it has got the same distribution, and the model behaves according to matrix Q. and so on and so on. And based on the behavior of this Markov chain or this generator matrix, we can evaluate the stationary distribution of the extended process. The stationary distribution of the extended process is a solution of a linear set of equations, which is characterized here. And based on this solution, one can compute the required measure, the time, the probability distribution of the Markov chain at time theta, according to this expression. Over here in the numerator, we compute the transition rate from state I to the extra state, which represents that the clock expires. In the denominator, we have got the transition rate that the clock expires. It can be obtained based on the stationary distribution of the extended process, which is characterized by gamma, and some additional parameters which are known from the process behavior. So basically, with this relation, we obtain the behavior of the model at time theta. But if time theta is such that the mean of theta is capital T and the coefficient of variation of theta is small, then the expected value of p theta is very, very close to the transient quantity at time t. So this is the general idea, and this idea can be also applied for Markov fluid models. Markov fluid models are coupled stochastic processes which are composed by a fluid part, a continuous part, and a discrete part. The discrete part is governed practically by a Markov chain with generator Q, and the continuous part is governed by the state of the Markov chain and the associated fluid rate. So in this particular case, when the Markov chain is in state I, the fluid increases at rate R sub I. After that, the chain moves to K, and the fluid changes with rate K. After that, it moves to state J. Fluid changes with rate R sub J, which is negative right here. And due to the fact that it spent a long time in state J, it reaches the boundary and it does not decrease below the boundary. And if it is a finite buffer model, then it is the same applies at the upper boundary. So this is the Markov fluid model, and we are interested in, okay, so this is the characterizing equations of the Markov fluid model. And so basically in the continuous part, the fluid, I got confused, sorry. X is the fluid and S is the discrete state. And in the continuous part, inside the 0B interval, the fluid changes at rate R sub I. And if we arrive at the boundary, then the fluid cannot go beyond the boundary. So it is limited at the boundary. Okay, sorry. The description of this model is by generator Q, which characterizes the state transitions of the continuous time Markov chain, and rate matrix R, which is composed by the diagonal elements R1, R2, and so on. The transient behavior of this fluid model is characterized by f tx, where t refers to the time, x refers to the fluid level. So basically f is the density at fluid level x, and one might compose a vector out of these quantities and this vector tends to a stationary fluid level as t goes to infinity. So basically, we would like to apply the same idea as before. Basically, what we would like to compute is a behavior which follows the original fluid model up to a random clock. After that, we have got a period of time which resets the model behavior to the initial state. Over here, we need to ensure that not only the discrete Markov chain is set back to the original state, but the fluid level is set back to the original state as well. And we analyze, we try to describe the behavior of this extended Markov chain. To do that, we compose something very similar as before. We are having an extended generator matrix, which is composed of the generator of the clock, matrix A, and the generator of the Markov chain, which is Q. And when the clock expires according to this transition rate, then we move to an additional extra state, which is to reset the Markov chain. And over here, we need to reset the Markov chain, which is ensured by a level-dependent generator and transition rate matrix. So basically, when we are in any fluid level X, we do not move immediately to the new interval, to the new cycle, but if X is less than A, then the fluid rate is +1, so the fluid starts increasing towards level A. If X was greater than A, then the fluid level has to be decreased until it reaches level A. Whenever we reach level A, we apply this exponential time to restart the model, which is restarted in state I, and the clock is initiated with vector alpha. So basically, this fluid level dependent set of generators characterizes or ensures this behavior. So basically, the process remains in this state 0 until it reaches level A, plus for an exponential distributed time with parameter 1. Anyhow, based on the behavior of this extended fluid process, one can compute the parameters again by considering the transition rates from a given state to the extra state, which represents the expiration of the clock. Again, the concept is that the extended model, the stationary behavior of the extended model is known, and when the stationary behavior of this model is known, one can approximate the behavior of the model at the expiration of the random clock. And if this random clock is very concentrated, then it is a very good approximate of the transient behavior of that time. It is just to mention that we need to apply this representation, and we might apply it such that the pi vector is this eta I parameters, and the A matrix is just diagonal with the beta I parameters. But additionally, one can apply any transformation from this complex representation to real representation, in which case pi and I is going to be real. Finally, the application of concentrated matrix exponential distributions for Laplace transformation. Okay, over here, having a function h of t, the Laplace transform is defined as h star of s, which is obtained by this integral. We assume that this integral is finite for all s, which is a complex variable, for all s whose real part is positive, and additionally we assume that h of t is real, which also has got some consequences on the Laplace transform, namely that the Laplace transform of the complex conjugate of s is going to be the complex conjugate of the function at s, which allows us to compute this sum quite easily. So basically this sum can be computed based on one evaluation of the Laplace transform function. Anyhow, there are several approaches for inverse Laplace transformation, and I don't know, not that long time ago, in 2006, Abate and Whitt provided a framework, or provided a paper in which they recommended to classify many methods in a particular framework. And in their framework, the approximate of the original function at point capital T is computed based on the Laplace transform with some coefficients eta k and beta k, and summed up this way. Okay, beta k's are referred to as nodes and eta k's are referred to as weights, and basically a lot of known Laplace transform, inverse Laplace transformation methods are based on this scheme, or this framework, which we refer to as Abate-Whitt framework. So these procedures basically differ based on the definition of eta k and beta k. Some of these well-known methods, the Geiger-Scheffers methods, which defines these eta k, beta k parameters according to this scheme. Over here, the important point is that all of these are real. The Euler method, which defines the parameters according to this scheme, this small I represents the complex units. Over here, the sum of the parameters are complex. The third method is the Talbot method, which characterizes again the eta beta parameters according to a given well-defined expression, again with some complex weights. This plot indicates the location of the parameters. So the Geiger is real, the Euler is one real, and the rest are complex, and the same with the Talbot. But the Talbot is such that it uses nodes with negative real part, and in one of the first assumptions, we assume that the Laplace transform is not available with the negative real part, and so this way we just exclude those cases which would go for a substitution of the Laplace transform function as the complex number with negative real part. Anyhow, the main point which comes from the Abate-Whitt framework, actually it is not very much applied till now, that just simply this expression can be rewritten according to the definition of the Laplace transform. So this is the definition of the Laplace transform as point bk over t. So having this expression and interchanging the parameters, we obtain an expression of this form. Basically, or better to say, an expression of this form where we are interchanging the integral and the summation, we obtain this expression in which we have a function like that. It is what we called f and t, where f and t is used for an integration, which gives you the inverse Laplace transform value at point t according to order n. And this integral basically uses the whole ht function from 0 to infinity, and it weights it according to this f and t function. It is quite obvious that if f and t was a unit impulse at point t, then at point 1, then this integral would result in ht without any error. So basically what we have here is that one can try to set f and t to approximate the Dirac impulse at point 1, and if it is it's a proper approximation of the Dirac impulse at point 1, then this integral will approximate the function of age at point 1 very closely. Over here we have got the so-called f and t function of different procedures, which I mentioned earlier. The Euler, which has got complex eigenvalues, we can see that it results in quite big waves. It's much sharper at 1, but on the price of having some significant waves far from 1. The Geiger method, it's rather slow. It has got the real eigenvalues, and it still has got some negative terms over here. And as a result of this f and t function, actually just interpreting the f and t function and the integral, which we refer to as the integral interpretation of the inverse Laplace transform, one obtains this behavior for the unit step function. So basically, instead of having just one jump, each of these functions has got some undershoot and overshoot, and the more sharply changing procedure, the Euler method, has got more significant overshoot, and it has got some oscillation at the discontinuities of the function. So basically, just due to the same expression which we have used earlier, we have got a matrix exponential, a concentrated matrix exponential function, which can be written in exactly the same manner. So it can also be used as an f and t function for the inverse Laplace transformation. There is an example how it looks in case of a low order. I mean, it is the same as we discussed. It has got a peak, and it is shifted. Actually, this peak is, if it is properly shifted, it is at 1. And you have got some waves here, and some might be here. But the key point is that it is strictly non-negative. This is compared to the other two functions. So over here, the continuous line is the matrix exponential for order 10 and order 20. And the matrix exponential is not as sharp in increasing at 1 as the Euler, but it does not have that significant oscillation as Euler has farther from 1. We made some tests using the concentrated matrix exponential function, which is used for inverse Laplace transformation. So basically, we named the procedure when we use the concentrated matrix exponential as CME method, and we compare the behavior of the method with these kind of test functions. And there are some plots about the behavior. So basically, after a given order, this Geiger method starts having numerical difficulties. The Euler method starts having very significant waves, while the CME method, due to the non-negative FNT function, is free from undershoot and overshoot, and is, as the order increases, the function approximates better and better the square wave function without having any artifacts as it is depicted here. I need to mention that this artifact is due to numerical instability. So basically all of these figures are using standard double precision, and the Geiger method is most sensitive to numerical error. The Euler method over here, it is not the numerical problem, it is just the waves generated by the very wavy FNT function, while over here we have got the standard double precision up to order 500, and it results in very stable behavior. Same kind of results for the shifted exponential function. Again, significant wave develops for the Euler method, and these waves are not present in the case of the CME method. This table summarizes the behavior for a kind of distance. So over here we check the distance of the known time domain function and the approximate or the inverse the function which is computed by the numerical inverse Laplace transformation over a given interval for those functions which are listed previously. And we should mention one thing which turned out to be interesting. For all functions which has got discontinuity, the CME is the best. And also in the case when the other suffers from significant numerical errors, the CME is the best. But for smooth function, in this case, like the sine function, the Euler method behaves better. So this is the summary of the inverse Laplace transformation part, and I'd like to introduce you this website where one can play around with various kind of functions. Basically, the one which I represented here. I just need to figure out if I can switch to. I'm wondering if you can see these. Okay, why? I'm going to share my whole screen. Can I ask for a feedback if you see my browser right now? Anyone in the line? No.
I can see.
Yeah, thanks. So basically, just on this web page, we try to summarize and make it easily available these functions, and it contains a kind of demo. So over here, you might choose any of these functions. Actually, one can define any function here, but using the built-in ones, I can switch to the periodic square wave function, and we can plot it from 0 to 10 in this number of points in order 20. So it is the result for order 20. What can we see? Okay, so somehow the Geiger gets to be flat out at the mean quite soon. The Euler having this waving behavior, and the CME procedure, the red line, is just taking some kind of alternating behavior similar to the Euler one, but a bit with a bit less amplitude, and does not have overshoot, neither undershoot. It is also referred to as Gibbs oscillation. So this CME is free of Gibbs oscillation. If I keep increasing the order, the giver starts having numerical issues. So I just switch this off, and we have got this kind of strongly waving behavior for the Euler, while we have got better and better approximate with the CME, and increasing further on the order, we have got extreme waving behavior with Euler. So after some point in time, it gets to be completely meaningless. And I just would like to demonstrate that going further on with the Euler, with the CME method, we can use, we can obtain very, very precise results using the standard double precision, in which case I can go up to, I think, 400. It takes a longer time, but you get rather accurate approximation of the square wave function. So basically, this was all. And yeah, basically, I just wanted to summarize some results, namely that one can generate concentrated matrix exponential distribution with very low coefficient of variation. Practically, the coefficient of variation is less than 1 over n squared. And one can use this concentrated matrix exponential distribution using, I mean, computing various transient measures of stochastic models. And additionally, it can also be used for numerical inverse Laplace transformation. So I think it was all. Thanks for your attention. And I am open to questions if you have.
Thank you so much. Thank you so much for a very interesting and impressive talk. And especially I would highlight the last point, because I was trying to ask if there is a software implementation of that. So, but I guess it is. And I mean, so at the site, we can play with it and see what happens.
Yeah, so yeah. I think it also, all the links are, this repository contains the software implementation in various languages.
Yeah, that is great. Thank you so much. Thank you again. And please proceed with questions. I will address mine at the end of, if any other.
I have a question, if I may.
Sure.
Miklós, it's Rostislav.
Yeah.
So glad to see you. Thank you for your talk. Well, for me, you know, it was very interesting to see that there is a relation between the fields, which for me, at first glance, seemed to be not related. So it was really interesting. And the short question. So at the very beginning, you mentioned that the squared coefficient of variation for this concentrated matrix exponential distribution is big O of 1 divided by n squared. Is it so?
Yeah.
Yeah, big O. Yeah. So it means that there is a constant inside this big O.
Yeah. Yeah.
So is it possible, or is it meaningful to have an estimation about this constant? So, or did you think about it? I just made some numerical things, and it seems like it is less than 2, for example.
So, okay. So basically, what we have is always changing with the order we can compute. So up to 47, we had got this kind of estimate for the experienced numbers. Going above 47, over here, you can just approximate these. I mean, of course, we have got all the numbers. It should be less, so the exponent is greater than 2, and the coefficient is practically 1. So there is no trick with the coefficient. I mean, the coefficient does not increase. And as we are able to compute, but this is already a kind of optimization. So I would say that the theoretical optimum definitely has to be less than the solid line. But the solid line decays approximately with 2, a bit, the order is a bit larger, so like 2.1, something like that. But I think if we can compute this for 2 more orders of magnitude, you might get even lower coefficient or whatever, sharper decrease then. So basically, I am sure that 1 over n square is larger than the minimum of the coefficient of variation.
Thank you. Thank you. Now it's more or less clear. Yeah.
Any more questions? Yeah, I had one. Maybe just curious, maybe even 2, okay, if you allow. So just curious if it is meaningful. I mean, so you told that the order of 1 divided by n, the squared coefficient of variation 1 divided by n for the phase type representation, right?
Yeah.
So, but it is so the phase types that are independent of each other, right? So we just sum up some independent random
exponential.
Yeah.
With the same rate.
Is it meaningful to do they in some sense dependent to like, let's say how it is done in some variance reduction techniques where you do some dependence that reduces the variance? Maybe in this case it will also result in the decreasing of this squared coefficient of variation, or it is meaningless. I mean, I don't know, but just curious.
Okay, so I mean, remaining in the phase type family, it is this is a quite well-known result. So if you leave the phase type family, I think one obvious direction to leave the phase type family is to relax the sign constraint, and you arrive to the matrix exponential class, and that's what I was talking about. If you leave the phase type family to some other directions, I think these are all options to play with or try with. It is just that you need to have a methodology which is applicable in some ways. So the nice property of the matrix exponential family is that you can implement them in the presented way in stochastic models or in Laplace transformation or inverse Laplace transformation. But there might be techniques, variance reduction techniques, which are useful, more efficient, and still applicable. I mean, I don't know such techniques, but yeah, it might be the case.
Yes, and maybe a short one. So if it's quite popular now to use these neural networks in the context of optimization problems. So since you are using also some optimization, what do you feel? Is it possible or kind of fruitful to use this type of techniques for continuous of your research, or no?
I would say that these dates indicate how much we struggled with obtaining these results. We tried quite many optimization techniques and ways, and we found many of them not appropriate for this problem. I know that the methodology with respect to neural networks based optimization is continuously developing, so it might be the case that recently there are some more efficient methods, but when we tried, they did not help. It was quite a long time for us to find these evolutionary strategies which helped us out. We tried quite many ways to optimize this problem. So it might be the case, but when we arrived to this, why we arrived to this, we tried many and they did not help.
Yes, thank you so much. Thank you again. Any more questions, please?
Just a short question, if I may, related to your question, Alexander. So, Miklós, could you please, if it exists, what was the main problem in this numerical solution of the optimization problem? Is there any specific one which is the most difficult? Maybe exhaustive search of the values of coefficients, or what's the most difficult?
I think it is a surface with very deep holes in it.
Mm-hmm.
And you need to jump. I mean, these optimization procedures might jump to one of the hole, but it might not be the optimal one.
Mm-hmm.
And yeah, these methods practically could not come out of the.
So it was a danger that you got stuck in the local minimum.
Yeah, and there are very bad local minimums. So yeah,
which seem like global.
Which the optimization procedure could not get around or get stuck in it. So basically, the way we worked is that, okay, up to, I don't know, we had got these points up to 2006, and we tried with many other going further on, and the way for us was that we believe that is going to continue. So we believe that it is not that it stops at, I don't know, 17 and it remains horizontal after that. So we started with one method and other method and other method, and we never could exceed this one at 17 until we got into this evolution strategy, which helped us out. After that, we arrived there, and actually we used the simple version of the evolution strategy at this interval. We arrived here and we could not improve anymore. And again, the same concept that we went on and we jumped to, I don't know, from one procedure to the other, and we wanted the curve to follow. And again, with this heuristic, so it was quite obvious that after some time you just couldn't optimize all the parameters. So we needed some smart limited parameter optimization procedure. And we were very happy to see that it's practically along the same trend. It's a bit higher than the minimum. So that's, that was the way for us. Always, we compare the results with the previous one projected to that point.
And maybe the last question, sorry, about the F plus with index n. F plus. So you mentioned that, so this is, you just picked up this function because of the conjecture. And the question is, probably, maybe you answered, but I need to ask. So this F plus n function, this F plus t, okay. So if we convert F plus t into the matrix exponential distribution, so do we have the probabilistic interpretation of the coefficients? No. Okay.
With matrix exponential, you have no probabilistic interpretation.
Even if this F plus t is taken, so even for it. So we're not lucky.
I don't have any.
I thought that maybe since it is a special class of functions, maybe for it there exists a probabilistic, but still no. Okay, thank you.
No. The only point which might be mentioned is the location of the eigenvalues of this guy, and practically it is not plotted here, but it is the same as for the Euler. So it is one real and all the others. Actually, these are complex conjugate pairs, but only one of the complex conjugate pairs with positive imaginary part is depicted in this figure. So basically, the eigenvalues are very similar to the Euler one.
Thank you, Miklós. Thank you.
You're welcome.
Yeah, thank you so much. So it's an open problem, right? To address.
I mean, to prove that it is minimal, it is an open problem, even for n equal to 3.
Oh, I see. So many open problems. And the other one is to get the probabilistic interpretation of that, right?
I can tell you that one of the reasons for not being able to obtain any practical result along this line from 2006 to 2016 was the fact that we wanted to prove it. And we couldn't. We just failed. We just couldn't prove it.
Yeah, sure.